Okay, welcome back for part two of three-dimensional shapes of molecules. And now we're going to walk through all of the possible combinations of electron geometries and the molecular geometries that can come from those. So we saw this slide last time indicating that Lewis dot structure, which can be determined from the molecular formula, tells us the number of groups of electrons around a central atom. And the number of groups of electrons directly gives us the electron geometry based on VSEPR theory, valence shell electron pair repulsion, that electron pairs or groups try to get as far apart from one another as possible. And we said if all of the electron groups around a central atom are bonding groups, then the molecular geometry, or the shape of the molecule, is the same as the electron geometry. But if one or more electron groups are non-bonding electrons, that is, there are lone pairs of electrons on the central atom, then the molecular geometry, or the shape, is different from the electron geometry. So now we're going to walk through all of the examples. So first we'll look at all of the cases where there are four groups of electrons on the central atom. In all of these cases, the electron geometry is tetrahedral. So this shape here that you see is tetrahedral, where one way to think of it is three of the domains are pointing down at different angles away from each other, and one is pointing straight up. And the bond angles are 109.5 degrees. So if there are four bonding groups, that is, all four electron groups are bonding groups, then we said the molecular geometry is the same as the electron geometry. Here's an example like CH4, right? The Lewis dot structure looks like this, right? So we see four electron groups, all of them are bonding, and so it looks still, the shape is tetrahedral. Another way to draw this is using the wedges and dashes. So if I try to say like this, H is coming out of the board, and this one is going back. Right, this is my attempt to draw this, right? So that's tetrahedral shape. Now, ammonia, or NH3, is an example of the next step down in our diagram. If we have four groups of electrons, but only three are bonding groups, and there's one non-bonding group, right? The lone pair on the nitrogen, we now have trigonal pyramidal. So how did that come about? The electron geometry, as we see here, still has four groups, right? The electron pair at the top happens to be one of the groups. Because it's there, all of the groups will be separated by 109.5 degrees. However, when we think about the shape, we don't take into account electrons, so all that's left over are the atoms. And so we see three hydrogen atoms pointing slightly down from the nitrogen atom in the center, and the shape ends up looking like a pyramid with three sides. That's why it's called trigonal pyramidal. The bond angles are still the same because that's determined by the electron geometry. Okay, continuing down, let's say we remove one more bond and we have four groups of electrons, but 2 bonding to non-bonding, like water, for example. So the electron geometry, this whole group, right, they're still tetrahedral, but now 2 of those spots are taken up by simply electrons. And so when we look at the shape, those are left out, and what's left over are the 2 hydrogens pointing down at an angle from the oxygen. And so the shape is bent, right? It's a bent shape, not linear. And this angle is 109.5 degrees, approximately. Okay, so that's all the possible combinations of 4 groups of electrons and then different numbers of bonding pairs. Let's move over to the next column. And if we have 3 groups of electrons around the central atom, well, if all 3 groups are bonding groups, then the molecular geometry, or the shape, is the same as the electron geometry. And so that's trigonal planar. Formaldehyde is our example here, where carbon has a double bond to this. So that still counts as just 1 bonding group. And then there are bonds to these other 2 hydrogens. And so there's 3 total bonding groups, and they will separate out 120 degrees from each other, and we get trigonal planar. Now imagine one of these bonded atoms removed and replaced with a lone pair. And that's the next case. So sulfur dioxide has an expanded octet, so it actually can make 2 double bonds and have a non-bonding group. So there are 3 total bonding groups, and 2 are bonding and 1 is non-bonding, right? And so if we replace what was there before with just simply electrons, what's left over in the shape from atoms is a bent molecular shape. Now notice that this is different than the water bent shape, because water bent shape came from a tetrahedral electron geometry and had an angle of 109.5. Sulfur dioxide here comes bent shape from 3 groups, or trigonal planar, and so this is 120 degrees. So it's a subtle difference, but it is a difference, and it is because of the the electron groups that are present. Okay, we can't remove any more and still have a shape, so we'll move on to the final case where we have 2 groups of electrons. So hydrogen cyanide would be an example here. Also an example is carbon dioxide, which they have 2 groups of electrons. Both are bonding, and so it's linear. So I told you we're going to walk through all of the possible combinations for 2, 3, and 4 groups of electrons, and we did. This is it. So it's all summarized succinctly in one single table, which is on page 122 of your textbook. And you'll see the same things that we just did, but it's kind of nice to see it here in table form. Notice that this column, number of electron groups, is equal to the number of bonding groups plus the number of non-bonding groups. So 4 can be 4 and 0, 3 and 1, or 2 and 2. 3 can be 3, 0, 2 and 1, and 2 can only be 2 and 0. And we see all of the similar examples is the Lewis dot structures and the three-dimensional ball and stick model. So this would be a good table to spend some time looking at. Now remember, you don't have to have this memorized, but you should be able to look at it, or look at a structure, and figure out the molecular geometry. The sequence, once again, is molecular formula. Gives us Lewis structures. From Lewis structure, we can get electron geometry. And from electron geometry, we can get shape, also known as molecular geometry. Okay, one last thing here about bond angles specifically. Bond angles are not given on this chart, but we did talk about them in our walkthrough. So here we go again. Molecular bond angles are determined by electron geometry. So it doesn't really matter exactly what the shape is. What matters is the electron geometry that it came from. So if it's a tetrahedral electron geometry, the angle is 109.5, regardless of if there are lone pairs or not. So that would be trigonal, pyramidal, and bent from 4 would be the same angle. Trigonal planar is 120 degrees, which is also true for bent from 3, and then linear is 180. So there's basically these three main groupings of angles that come from the three electron geometries. Okay, in the last part, we will come back and do a couple examples together.